I am honored to introduce Professor Walter G. Chapman. Professor Chapman graduated at Clemson University, where he received his bachelor's degree in chemical engineering. He then received his PhD degree, also in chemical engineering, at Cornell University. Before becoming a professor, he spent 2 years as a research engineer with Shell Development Company. He's currently the William W. Akers Chair Professor, the Director of the Energy and Environmental System Institute, and the Associate Dean for Energy Research at Rice University, Texas, United States. Professor Chapman has an interest on the development of statistical mechanics-based molecular theory to study structure, properties, relations in complex fluids. This also refers to molecular simulations, NMR, and other experimental techniques to validate the models. Some of his current research interests include polymer solutions, blends, associating fluids, confined fluids, and electrolytes. Among his several contributions, Professor Chapman is famous for the development of an equation of states for associating fluids called SAFT. Together, his three main papers about equation of states for modeling associating fluids. Together, they have more than 5,600 citations. Nowadays, Professor Chapman has more than 292 publications with more than 12,600 citations. So before starting, I would like to show again Professor Chapman. No, I see that, but okay, no problem. Just to show a picture of Professor Papa and Professor Chapman in 2002. Okay, just to show. I will share my screen. And I would like to thank Professor Chapman in advance. And well, we are here to learning from you. Let us know if you need any help, okay? And thank you.
All right.
Thank you very much.
Great, thank you. And thank you so much for the invitation to present today. Fred asked me to present some things to first-year thermodynamics graduate students, and so I'll go over some review material. But I also thought I would just put in some things that I guess I've learned while in graduate school or over the years that I think it would be good for students to know and to learn. So I'm going to talk about statistical mechanics, and particularly statistical thermodynamics, and so applications of those, and then a brief overview of some things that I've learned. Statistical thermodynamics is a science in which you relate intermolecular forces to macroscopic properties of fluids, and so it's a very powerful area of science. And I'll tell you a little bit more as we go on. I thought I'd tell you a little bit about Houston. This is way back here is the downtown area of Houston. In the foreground is the Texas Medical Center, and Rice University is right here in this kind of green area. So we're located across the street from one of the largest parks in Houston, and across the street from this Texas Medical Center. Houston's known for a number of things. We're the home to NASA. We're considered to be the energy capital of the world. There are 5,000 energy-related firms throughout Houston. This medical center is the world's largest, and so we're very proud of that. We have a large port. Although Houston is 45 miles from the ocean, it's still one of the largest ports in the United States. And it's interesting, Houston's 45 miles from the ocean, and we're about 45 feet, maybe 50 feet of elevation. So you can tell Houston's incredibly flat. We also, because of this ship channel that comes into the city, we're have the second largest concentration of chemical companies in the world. Houston is very diverse. There are 90 languages spoken in Houston, and 92 countries have consular offices in Houston. So that means when I want to travel to Brazil, if I need a visa or anything, I can just go to the Brazilian consulate. So it's very convenient. So I thought I'd share some things that I've learned. And so forgive me, but I'll just go through some of these as bullet points. The first is that as you are studying different systems, what you find is the physics is really the same in many systems. And so you can, in many cases, relate the physics to systems that you know. And so I find it very convenient to think in terms of examples, real world examples. For example, when I teach phase behavior, I tell the students to think about the weather, because you experience the weather all the time. The atmosphere is just a mixture of gases, including water, and sometimes the water precipitates. And so thinking in terms of these terms, I think allows you to hopefully understand subjects like thermodynamics more reasonably. The second thing I learned was to think physically about a system, not in terms of equations. We can write down equations, but it's really important to think in physical terms. You see this in transport phenomena commonly, where they have dimensionless groups. You know, for example, ratio of diffusion versus convection, or other terms. And so you can identify what term in the equation, what it physically means. And the more you can do that, the better you can interpret, and the better you can work with the theory. Third, I'm going to say there's less data than you think, and not all data is of good quality. I've seen also many cases where people say, oh, this data is old, it's probably not good. And that's not true. So what you're going to find is some old data, I can think of authors like Olds, Sage, and Lacey, Kobayashi, and others. The data is actually some of the highest quality data. So what's going to happen is you get to know some of the authors, and you'll learn who develops quality data. Here are thermodynamic laws. I say are not limited to molecules. Actually, thermodynamics are 3 laws that were written down before it was understood what atoms, what the correct model of an atom actually was. They're written down, they're general ideas, general laws of nature. And so you can apply these to colloids. You can apply it, and people do, to information technology. And you can apply it to people. And so what you find is people actually, the way they behave, you can describe in terms of thermodynamics. So I'll try to show you an example. Another point, the motto of the Royal Society in Britain, it's written in Latin. But what it means is, it means take nobody's word for it. In other words, prove things to yourself. Or this is the way I read it. As engineers and scientists, we have the tools. And so what I found is that in some cases, the things that people assume are correct, or that they've learned over the years are correct, aren't necessarily always correct. So if you have a hunch, prove it to yourself. When I worked for Shell, I know that when we were told that roughly 5 to 10% of our time we could work on anything we wanted. And sometimes you could work on things that turned into great new advances. Other times you worked on something and it didn't work out, but you were always learning. So go through and try to prove things to yourself. Another is simplify problems. Look at limiting behavior. As you are developing models, theory, or doing experiments, you always need to be able to touch base and figure out, is what I'm doing, does it really make sense? And so if you can simplify the problem, look at simplified cases, or relate it again to something you've seen before, it really helps. I know faculty have graduate students working on many interesting projects, and the graduate students come with results, and the faculty member has to judge whether the results are correct or not. And so what the faculty member, one thing the faculty member does is they think about limiting behavior. They think about, attaching it to something they know is true. And just to at least have a touch point that what the right thing is. Another thing I know, when I was in graduate school, I remember the first project I had, I gave the answer to my advisor, and as a student, I thought, well, okay, is he going to tell me if I'm right or not? He's going to grade it. When you're graduate school, your advisor doesn't know the answer. That's the reason to do the research, right? But again, you want to verify, you want to make sure that your results are right. And so looking at limiting behavior, simplifying the problem, and just having a touch base really helps. Another point, this is in John Prousness's book. He says that one of the outstanding characteristics of great contributors to modern science has been their ability to distinguish between what is essential and what is incidental. And I think that's a very good way of looking at things. In other words, it's the same idea. Simplify the problem. To only look at the essential features and understand how they affect the problem. Okay, so I'm going to talk about phase equilibrium. You've probably seen these sorts of things, but I'll just go through it quickly. So I'm interested in phase equilibrium. Why? Because we're interested in separations, maybe vapor, liquid, 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 or solid, liquid, equilibria. Why is that? Because in a typical chemical plant, roughly 50% of capital expenditures is related to separations. In pharmaceuticals, it can be 90%. There's other reasons to look at phase equilibrium, and that's because you can have unwanted phase splitting. For example, you can have deposition in heat exchangers or pipelines. And this may be due to scale, like electrolytes, mineral scale. You have polymers, wax, gas hydrates, asphaltenes. In other cases, you may have phase splitting in reactors, and this can result in poor product properties. There's one example I remember at a conference, a fellow who's an expert in thermodynamics at Exxon said that they had a polymer solution process. I think it was for making polyethylene. But he said that you always stop the process at a certain conversion. And he said, he doesn't know, he's not sure that people really know why that is. It's just known that you stop at a certain conversion. The reason is, if you go beyond that conversion, you undergo phase splitting in the reactor, a liquid-liquid phase split. And that can result in poor molecular weight distribution of the polymer. And so you want to avoid that. In other cases, for example, if you're making a polymer foam, you're interested in having phase splitting, but you want to control it so that you can generate a foam with the bubble sizes of the right distributions. The other reasons we're interested in phase behavior, it's used in production of soft materials like through self-assembly. It's important in drug effectiveness as well as in drug delivery. You see now that a lot of pharmaceuticals are in bubble packs. So you've got a metallized sheet and then these bubbles of plastic and individual pills in each one of those. You might think, oh, that's convenient because I can just have one pill in one little container. The reason they do that is because humidity can affect the phase behavior in that pill. And if humidity, if the drug undergoes a phase transition, it can crystallize and then it will be ineffective. And so this is why there are use by dates And in some cases, you want to keep the pharmaceutical under very careful conditions, like low humidity. And of course, there are other reasons. So this is a quick overview. I'm going to start with something I'm sure you all familiar with, but it's essentially when we're doing phase behavior, we're setting up a balance. Just like you have energy balances or mass balances, here you have a chemical potential balance or fugacity balance. Simply says the fugacity of a component I in one phase has to be the same as fugacity component I in another phase. And we use different ways of calculating fugacity. In some cases, we calculate deviation from ideal gas behavior in terms of fugacity coefficients. In other cases, deviation from ideal solution behavior. And here we have an activity coefficient. And of course, we start off by looking at a system that may obey Raoult's law, for example, where there's no non-ideality in the gas phase and no non-ideality in the liquid phase. Of course, what does that mean? Well, non-ideality in the gas phase, or non-ideality with respect to an ideal gas, has to do with intermolecular interactions. So if you're under conditions where you can have strong intermolecular interactions, then you'll have large deviation from ideal gas behavior. And a liquid, for example, is that case, where you're at low enough temperature that the attractions between the molecules put you in a liquid state. In that case, it's sometimes convenient to use an activity coefficient. An activity coefficient tells us deviation from ideal solution behavior. An ideal solution is one in which the intermolecular forces between the molecules are literally identical. I tell my students, you can have red methane and green methane, or red butane and green butane. The forces of interaction are the same, but the colors are different. And because the colors are different, it can mix, it will mix, but as far as the molecules are concerned, they only feel the forces. And so it forms an ideal solution. But if you mix something like an alcohol with a normal alkane, the alcohol has certain interactions that are different from the alkane's interactions. And so then you can have large deviation from ideal solution behavior. So let's look at some phase diagrams, and just as an example to show this. This is a simple system. It's called class 1. It's argon and krypton. On the vertical axis is pressure. On the horizontal axis is mole fraction, either in the liquid phase or the vapor phase. And going back into the page is temperature. And I want to show this because really it was in graduate school I became to realize that this is actually a three-dimensional phase envelope. And this is actually from figures that the wife of my advisor drew. And this is some slides I took from North Carolina State University from Keith Gubbins' group. What we usually see is we see slices through this three-dimensional phase diagram. So a slice at constant temperature, for example, or then this slice here is at constant pressure. We usually look at two-dimensional slices like these and plot them this way. But you need to realize that there's a temperature axis that's going back into the board or back into the page, and that's what gives the shape here. And so it's interesting just to see the relationship between these constant temperature slices or constant pressure slices and what the phase envelope looks like here. That's class 1, and in this case, these components form a nearly ideal solution. You can see the pressure times versus liquid composition. Here is a linear curve. We're interested in less ideal cases. For example, here is normal hexane with aniline, and not only do you have a region of vapor-liquid equilibrium, but there's also a region of liquid-liquid phase split here. So at low pressures, you may be in a vapor-liquid region, but as you increase pressure, there's a region where the two liquid phases split. And that's not because of repulsions between the molecules, but it's because of attractions between the molecules. The normal hexane is a normal alkane. Aniline is a benzene ring with a nitrogen on it. It has polar interactions. And this charge distribution in the aniline allows aniline molecules to attract each other more strongly than they interact with the normal hexane. And because of that, aniline prefers to be in its own phase. When I talk to students to explain liquid-liquid phase splitting, I think in terms of there's differences in interaction. And a good example of that is boys and girls at a middle school dance, right? Because boys and girls at a middle school dance, there's not repulsion between the boys and the girls. There's, in fact, some attraction. But all the boys go to one side of the room, the girls go to the other side of the room. Okay, there's a little bit of mixing. There may be a little bit of dancing in between. But what you see is there's a phase splitting just because of slight differences, or maybe major differences, but differences in interactions. And so I would claim that this is really just thermodynamics. Now you can find even more interesting cases. This is now class 3, but it's called gas immiscibility of the second kind. In all of these cases, it contains water with benzene or ethane or xenon, methane. And what happens here is you can have vapor-liquid equilibrium at low pressure. At higher pressures, you can have liquid-liquid splitting. But what's interesting is as you increase the temperature, you can be above the critical temperature for component A, which is on this side, or component B, which is on that side of the curve. And so you can be supercritical to both A and B, but you can have a phase split. Usually we think of, if you have two gases, they're going to mix in all proportions. But at high pressure, the densities of the gases are approaching the density of a liquid. And at a liquid-like density, these components could phase split. And that's exactly what happens. So what I've tried to do is give you a quick overview of some of the phase behavior we're interested in. But we're interested in this phase behavior as well as interfacial properties and self-assembly, with some applications being separations, deposition, and with self-assembly to maybe to create interesting nanomaterials, or what they call soft materials. The challenges, both in the upstream, which is production of oil and gas, downstream, which is petrochemicals, or could be in the biorefining area, is that we can have, say, large ranges of temperature and pressure. We may have polar components like ethers, esters, carbon monoxide, hydrogen sulfide. These components have permanent charge distributions in them. Carbon monoxide, for example, the oxygen grabs electrons from the carbon, so the oxygen is partially negatively charged. The carbon is partially positively charged, and so you have a dipolar interaction, right? Which is different from maybe some of the alkanes, which have very weak charge distributions. We have association, like water can hydrogen bond, alcohols can hydrogen bond to each other. We have large size asymmetry, like polymers or asphaltenes, and then there's brine chemistry. So you have charges on these electrolytes that can cause large differences or large deviations from, say, ideal solution behavior or ideal gas behavior, for that matter. Further, these molecules could be like surfactants. They may be amphiphilic in such a way that you're going to form, say, microdomains or interesting phases. And this can be used for product design or materials processing. So as an outline, what I've tried to do is give a bit of a motivation. I'm going to introduce some ideas in statistical mechanics, introduce equations of state, talk about some applications, and then do a summary and future work. So as a brief introduction, I realized this morning I hadn't included some of the basic equations of statistical mechanics. So forgive my handwriting, but I thought I would include some of these ideas. In statistical mechanics, first, statistical mechanics was developed by Boltzmann and Gibbs. And what they realized is that as molecules interact, and in fact, molecules, for the most part, can be described using Newton's equations of motion for molecules interacting with each other. The pressure in a fluid is given by collisions with say, a hypothetical wall, or maybe the wall of the container. But what happens is, at any instant in time, or any small delta t, you'll have a certain number of collisions. Over the next small interval of time, you'll have a different number of collisions. And so, in fact, the pressure varies, right? There's a distribution of pressures that you actually find. And so it's interesting, though, that in thermodynamics, we say that given a certain temperature and density of a fluid, we have a very specific pressure. Well, what we're actually saying is that there's a very specific average pressure. And what Boltzmann realized was there must be some very interesting averaging going on. Because if you look at every single different molecule, they all have different velocities. And yet, given the density and temperature, you're going to have a single pressure of the fluid. So somehow, all of this information about molecules moving around in this in three-dimensional space must average in some way. And so I'll just give you the summary. The answer is that's true, that the Helmholtz free energy is given by minus kT partition function, where we're specifying the number of molecules, the volume, and the temperature. The canonical partition function is given by, these are just some constants, but this is a multi-dimensional integral over the momenta of all of the n molecules in the system, or you can say integration over the velocities, if you'd like, of all the n molecules in the system, and integration over the positions of all the n molecules of the system. This is exponential minus beta. I apologize. I should have written this is minus 1 over kT. Beta is a shorthand for 1 over the Boltzmann's constant times temperature, so 1 over kT. And H is the energy of the system. So it's called the Hamiltonian. The energy is given by the kinetic energy in the system and the potential energy of the system, the total energy. For a simple, say, spherical molecule, we can easily write down that the energy is given by the average kinetic energy, or by the total kinetic energy of the system, and the total potential energy. So this is the potential of interaction of all the different molecules with each other. What we find is, I should have started here, what we find is if you substitute this Hamiltonian back into this expression, you'll find that you have this exponential of the momenta squared. And so exponential minus, say, momenta squared over 2m, where m is the mass, that's just a Gaussian. And we're integrating from minus infinity to plus infinity. And because the velocities or the momenta of each of the molecules is independent, we can perform that integral directly. And if we do, we end up with this term out front. But we still end up with this integral over the all possible positions of all the molecules and the potential energy of interaction between the molecules. And so what happens is this integral is incredibly difficult to do. So we solve it in different ways. One way of solving it is using what's called perturbation theory, where we say that I'm interested in the Helmholtz free energy of a certain system. I write down the Helmholtz free energy of a reference system, and then That's given by minus KT, the canonical partition function of the system of interest, divided by the canonical partition function of the reference system. And using some tricks, we're able to solve then for this, this ratio, or at least we hope we're able to do that. Let's consider a very simple system. Assume that the potential of interaction between molecules is 0. Then we have an ideal gas. If we have an ideal gas, the integration that we are performing over all possible positions of the molecules can occupy any position within a certain volume. So if the potential of interaction is 0, exponential of 0 is 1. This becomes integral over n volumes. And so we get a volume to the n power here. From that, we can write down the thermodynamics, like the free energy of an ideal gas, the chemical potential of an ideal gas, and of course the pressure of an ideal gas. PV is equal to nKT. So using these ideas from statistical mechanics, we get the results that we expect. That the Helmholtz free energy is here, the chemical potential is just KT log of the density times the de Broglie wavelength cubed, and PV is equal to nKT. So I'm hoping to give you an idea of how these equations, where these equations come from. Another way of solving for the thermodynamics of the system is by using what's called molecular simulation. In molecular simulation, we can either use Metropolis Monte Carlo or molecular dynamics. I'll talk about molecular dynamics. In that, we put all the molecules into a box on the computer, and we literally solve Newton's equations of motion for the molecules interacting with each other. And this allows us to obtain equilibrium as well as non-equilibrium properties of the fluid. So again, we can calculate the collision of a molecule with the wall of the box, and that tells us what the pressure is. We can calculate things like the internal energy of the fluid. We can also calculate the chemical potential, and that allows us to do phase equilibrium calculations within a molecular simulation. This is a brute force way of doing calculations, and it takes hours, days, or weeks in some cases to converge the solution. But it's a very powerful approach because it allows us, given the intermolecular forces, to calculate the property of the fluid. And this is also very useful when we're developing theory, because as we develop theory, we can define a potential model and use molecular simulation to obtain thermodynamic properties for that very specific potential of interaction. We don't know exactly how molecules interact with each other. We're still learning to get that information from quantum mechanics, and we're getting better at it. And if we could get all the forces of interaction from quantum mechanics, we could use molecular simulation to calculate the thermodynamic properties and transport properties of a fluid. But we also could use theory to calculate the properties of fluid. But we first need to validate the theory. So what we do is we perform molecular simulation for exactly the same force model as we're using in the theory, because the force model is the identical between the two. There are no adjustable parameters, and it's a rigorous test of the theory. So simulation provides a couple of different uses for us. So I want to get into thermodynamic models. And one of the early thermodynamic models is due to van der Waals. In fact, this is probably the first perturbation theory. So what van der Waals said was that the compressibility factor here, say pressure times volume over ideal gas constant times temperature, the pressure of the fluid is given by two terms. This first term is the compressibility factor of a one-dimensional hard sphere fluid. Molecules repel at short range, And a good model of repulsion is hard spheres, like billiard balls or ball bearings, right? And so van der Waals said that the equation of state of, say, simple molecules should be given by the pressure of a one-dimensional, of a hard sphere fluid. In this case, he only had the equation for a one-dimensional hard sphere fluid, plus the attractions between molecules. And these are attractions. Van der Waals didn't have the correct term at the time, but now these are called London dispersion forces. But because van der Waals essentially predicted them, they're also called van der Waals forces. So the pressure of the fluid is given by the repulsion, plus, in this case, the long-range attraction between the molecules. Now, van der Waals searched his entire career to correct this term, because this term is absolutely wrong. It's a one-dimensional hard sphere fluid. It's not a good approximation in 3 dimensions. As I said, this term is actually not too bad. And so in many cases, you could retain a term very much like this. Van der Waals wrote his thesis in 1873. Maxwell supposedly learned Dutch so he could read van der Waals' thesis in the original language. I think that's incredible, to learn Dutch just so you could read van der Waals' thesis. So in perturbation theory, what do? Well, we start with simple fluids, and we say that we're interested in more complex fluids, but maybe we know the properties of simple fluids. For example, we know the properties of a hard sphere fluid now, or a Lennard-Jones molecule, Lennard-Jones fluid. We actually have good equations of state. So we can develop models where if we know the property of the simple fluid, we can perform a perturbation to calculate the property of the complex fluid. Simple fluids typically are nearly spherical in molecular shape, and maybe weak attractive forces. And the properties depend on a single length scale, say the diameter of a sphere. Complex fluids have potentially strong directional attractive forces, like water that's hydrogen bonds here. They could have properties and structure depend on multiple length scales. For example, if you have a polymer, you have the length or maybe the radius of gyration of the polymer, plus you have the distance, the size of one of these individual segments. Or you could have polarity, dipole moments. You can have associating fluids. All of these make these systems non-ideal or more complex in some way. So they add to the complexity. So if we can develop a perturbation theory that uses a simple fluid to describe a complex fluid, then that would be very powerful. And this was done in the mid-1980s by a fellow named Michael Wertheim. And I extended this to develop an equation of state called SAFT. And Wertheim's approach, what he says is, imagine these two blue spheres are, for example, hard spheres. They repel each other. The red represents a hydrogen bonding site. For example, in water, this could be the 2 lone pairs of electrons on an oxygen. And this could be the hydrogen of another molecule. And the hydrogen of one molecule wants to associate, because the hydrogen tends to be positively charged, wants to associate with the negatively charged lone pair of electrons. And as you know, in hydrogen bonding, the hydrogen is actually shared between the 2 molecules. So what we're imagining is, this is highly orientationally specific and of short range. And so if these red blips overlap, for example, we describe that as a hydrogen bond. And so the potential of interaction might be sharply repulsive at short range because these are just hard spheres, but at intermediate range, the molecules attract each other. And this attraction can be very strong. What Wertheim recognized was that if these 2 molecules hydrogen bond to one another, no third molecule could come close enough to form a hydrogen bond. In other words, the hydrogen bonding is saturating. And in very hand-waving terms, this says that this is a 2-body interaction. You've probably heard that in quantum mechanics or in statistical mechanics, multi-body effects make things very complicated. Well, in this case, the system is reduced to only two-body interactions. So we solve this in the form of perturbation theory. We say the free energy, in this case residual to an ideal gas, is given by the free energy of a reference fluid, in this case maybe a hard spheres, plus the change in free energy due to association. And Wertheim writes this down for molecules with a single association site, and you end up with a very simple expression that the change in free energy due to association is given by an expression in terms of the fraction of beads, fraction of molecules that are monomers. And he writes, in this case, it really looks like a chemical equilibrium theory, and it in fact is, that the fraction of monomers plus the fraction that are dimers must equal 1. So the fraction of molecules that are dimerized, first to form a dimer, both spheres must, there need to be two spheres, and both spheres must be monomers. The density times this G of R tells you in the reference fluid what is the number of molecules that are in a certain range of a given molecule. And then this exponential function tells us the probability that the two molecules are close enough and they have a potential of interaction that's this hydrogen bonding potential. So this tells us the probability that the molecules are close enough and the temperature is right for them to form a bond. So again, the fraction of monomers plus the fraction that are dimers is equal to 1. So I'm going to skip this in terms of time, but what we can do is we can perform molecular simulations to verify this theory, how accurate this theory might be. And so what we do is we can decorate molecules with association sites and simulate the fluid. And what happens is the molecules associate with each other. And as they do, they form chains, for example. And what we find is a theory does very well in comparison with molecular simulation. In fact, so well that we can take the limit that the energy of association is very, very strong. In fact, covalent strength. And we can use that then to calculate the properties of molecules that are formed of chains of spheres. We can compare with molecular simulation results. Here for a hard chain fluid, these are 201 spheres bonded in chains. The compressibility factor versus density, so reduced density, going from ideal gas to a dense liquid state. And what we find is that we get excellent agreement for the equation of state. So what's the reference fluid is a fluid of hard spheres, but the theory is predicting the equation of state of polymer. Alternatively, these could be Lennard-Jones segments, and then we can predict the equation of state in very good agreement with molecular simulation. But once you form a chain, the chain can also hydrogen bond to other molecules, and this could be a model of an alcohol. And this forms the basis of what we call the Saft equation of state. The equation of state is then written as a perturbation theory. The free energy of the reference fluid is given by the free energy of the segments, plus the change in free energy due to chain formation, plus the change in free energy due to association. What's great about the theory is that the parameters are very simple. They're physical. We need to know the number of segments that make up a molecule. We need to know the diameter of a segment. We need to know the London dispersion energy, or van der Waals interaction between individual segments. And for hydrogen bonding, we also need to know the energy of association, which you can think of as a change in enthalpy of hydrogen bonding, and the bond volume, or the related to the entropy change of hydrogen bonding. This Saft equation of state is widely applied by a number of companies and to a wide range of systems. What it allows us to do is handle hydrogen bonding fluids and polymers that were not, there was no model that could handle before. I'm running short of time, and so Fred, I can stop here. I can go through one example.
You can go for an example more. That's
Okay.
very nice talk.
Okay, so let's talk about alcohol-alkane systems. An alcohol-alkane system, the reason this is of interest is because first, alcohols are used to inhibit gas hydrate formation. Gas hydrates can plug pipelines, and so alcohols are used as a freezing point depressant. But we need to understand the partitioning of alcohols into the hydrocarbon phase. It's also important for cryogenic gas processing because methanol is typically used to inhibit gas hydrates in energy production. And so when the natural gas is processed, methanol is still present in the fluid, and it can cause a bulge in the distillation column. And I can explain that maybe later. Alcohols are used in surfactant molecule manufacturing, and most thermodynamic models cannot match vapor-liquid equilibrium without showing false, vapor-liquid equilibrium without showing false liquid-liquid equilibrium. So let me show an example. Marco Sotiro suggested I look at this because these are so difficult to model with conventional activity coefficient models. So this is a case of butane with methanol. So this is pressure versus the liquid and vapor mole fraction of butane. And you can see that at concentrated butane, we have an azeotrope in each of these cases. You could ask, why does this occur? Well, the SAF model predicted this sort of phase behavior before I fit any parameters. But luckily, the model tells us not only about the phase behavior, pressure liquid composition here and pressure vapor composition, it also tells us something about the amount of hydrogen bonding that's occurring. So I'm going to blow up this case, and we're going to look at this case at 100 Celsius. At 100 Celsius, we see that we match the phase behavior very nicely, but we also see that at very low methanol concentration, where we have nearly pure butane, at very low methanol concentration, methanol, the monomer fraction of methanol on this axis goes to 1. And you can ask why that is. Well, if methanol is infinitely dilute, in other words, if there's only one methanol molecule in the whole system, then methanol cannot find any other methanol molecules to hydrogen bond to. In that case, you're losing an interaction. So let's strip methanol of its hydrogen bonding capability. If you strip methanol of its hydrogen bonding capability, it looks a lot more like ethane or methane than methanol. And so if I added methane or ethane to butane, what do we expect? Well, we expect that the pressure of the mixture the vapor pressure of the mixture should increase. Right? According to Raoult's law, that's what should happen. It should approach maybe the vapor pressure of ethane, which would be way up. I can't even reach it. But what happens is, as you add more and more methanol molecules to the system, then methanol finds other methanol molecules to hydrogen bond to, and the monomer fraction decreases. Now, what's interesting is that at the azeotrope, which is between a monomer fraction of 0.2 and a monomer fraction of 0.1, that in a monomer fraction of 0.2, the average cluster size of methanol is 2. But in a monomer fraction of 0.1, the average cluster size of methanol is 3. So again, if methanol, remove the hydrogen bonding, if methanol is like methane or ethane, it should take 2 to 3 methanols in a cluster to be the same as a butane. But that's where we see this azeotrope occurring. Now, if this kind of analysis is reasonable, then as we go to lower temperatures, then I should expect to find this 2 to 3 cluster size of methanol at lower and lower methanol concentrations. Because at lower temperatures, hydrogen bonding will be favored more and more. And that's what we found. as you go to lower and lower temperatures, that the methanol, the azeotrope moves to lower and lower methanol concentrations. We can take this further and look at other alcohols and alkanes. And we find, in fact, we predict the phase behavior very nicely. The dashed curves shows uniquac, but in uniquac, what was done was to match the infinite dilution activity coefficients. And what you find is a false liquid-liquid phase split in this case. Now you could match the data better if you didn't match the infinite dilution activity coefficients using uniquac, but SAF does an excellent job of matching the infinite dilution activity coefficients. And so it's reasonable to, say, apply that to uniquac, and you see that we're predicting false liquid-liquid equilibrium. The question is, are we describing the monomer fraction correctly? Well, for alcohols, groups like Gerd-Mauer's group and others have used FTIR, Fourier transfer infrared spectroscopy, to measure the fraction of free monomers in these systems. We didn't fit to the data. What we're doing is predicting what the monomer fractions should be. Here is a function of butanol concentration, or here is a function of propanol, here in normal heptane, here in normal hexane. And you can see that the model does an excellent job of predicting the extent of hydrogen bonding. Now, SAFT is actually a very simple model. The way SAFT looks at the fluid is it looks at what is the concentration of hydrogen bonding sites, or maybe OH groups, in the fluid. And so what we could do is we could replot this in terms of the same concentration of OH groups. If we do that, we expect that, again, the density of OH groups times the G of R gives us the number of OH groups in the neighborhood of an OH group of another molecule. And so we should be able to replot the data, and we know the temperature dependence, assuming that the association potential for all these different alcohols are the same. And so if we replot all that monomer fraction data on a single graph, here we have the fraction of free monomers, and here we have this ratio. This is actually the ratio of these exponentials. And you can see that all this data for the monomer fraction measured by these different groups falls on a single curve. And so what we're seeing, or I'm hoping we're seeing, is that the model is incorporating, is not only just incorporating the physics of the system, but is also giving us information about the system, about some of the consistency. So what we're able to do is accurately describe the activity coefficients. I didn't show that, but also the phase behavior. Avoids incorrect liquid-liquid equilibrium. It's a more predictive model. It provides consistent description of phase behavior as well as monomer fractions. And we can extend this to water content in hydrocarbons or polymers. It's a very powerful approximation that water in a hydrocarbon or in a polymer, in many cases, is at such low concentration that water behaves much more like methane or ethylene than water. And so you can actually reasonably accurately estimate the content of water in some of these hydrocarbon systems. Now, a lot of other stuff I was going to talk about, but I'll just say that SAFT, and I haven't talked about our density functional theory, but these are able to do is predict the effects of molecular size and shape, as well as association on phase behavior. And we can also use this to describe the microstructure of a fluid. In our ongoing research, we're doing this. We're studying self-assembly, for example, surfactants and blockopolymers forming micelles, the self-assembly in hyperbranch polymers, mixed patchy colloids, as well as fluid distribution, for example, in shale formations, where partitioning to nanopores becomes important. Understanding wettability, contact angles, and others. and trying to understand NMR behavior, in this case using molecular dynamics. And so I just acknowledge the support. These are some members of my group. Actually, several of them have now left, but I don't have a picture of the newer members. But at least give you an idea of who actually does the work. And so again, a summary. I'd be happy to answer any questions. I hope the time is okay.
Thank you, Walter. Very nice talk. And I think people enjoy. Let's see questions, please.
Turn my. So thank you very much, Professor. I think it was brilliant. I have a few questions here from some students. Gabriel is our student, and he's asking if you have or if you know about any reference where he can study in a didactic way about associating fluids. Well, your presentation was very didactic, and he wants more. Do you know any source of content he can check for more information?
Yes, let me.
I think in the seminar, you're going to talk more about this, yeah?
Yes, I'll talk more about the theories. Let's see. I was thinking there's yeah, for example, the early works here, this is in molecular physics. And I'll share the slides so you can have these, but some of the work is this work in molecular physics. There's work in industrial engineering, chemistry research. There are many different versions of SAFT, and so version I showed some results for is by Gross and Sadowski. In fact, I think I showed these are the different versions of SAFT, and I don't even have them all available. So, but they're all using the same association term, the same chain-free energy that that's presented in my PhD thesis, as well as in that molecular physics paper.
Okay, thank you. We have several questions here, but maybe some of them are more, well, probably some of them, it would be better if we ask you next Thursday.
Okay.
Well, let's see. Gerson is also a student here, and he wants to know about you, your opinion about the capable of predictions for some electrolyte models. Some, well, you didn't mention that in your presentation, but do you have something to mention about this capability of prediction for electrolytes?
Yes. So electrolytes are hard. We're currently working on electrolyte models. What we want to do is we want to be able to describe the hydration of ions, and because we're particularly interested in mixed solvent and mixed electrolyte systems. And so we believe that the competition for hydration of ions becomes important, particularly at higher concentrations of electrolytes and over ranges of temperatures. There are models that have been fit to match properties of electrolytes that are based on, say, chemical equilibrium theories. One is what's called scale-soft-Pitzer. It's actually developed at Rice, widely used in the energy industry. It's not a predictive model. It's based on fitting data to electrolytes. OLI is a company that has models for electrolytes that are commercially very useful, but again, they're fit to data, so they're not necessarily predictive. In develop a predictive model, I think we need to be able to handle both the short range as well as long range interactions with electrolytes. And we're interested in that not only to deal with simple electrolytes, but to deal with polyelectrolytes, polyampholytes, ionic surfactants, zwitterionic molecules. So it's an incredibly important area. Some of the models that are being used, there's one from Gabi Sadowski's group that uses just a Flory-Huggins or extended Flory-Huggins type term, and seems to do well. But I'm going to assume that it's limited when you're dealing with say mixed electrolytes or mixed solvent electrolytes, and maybe limited in concentration. It may also be limited in temperature. What's been found recently is that even molecular simulation models are not doing a good job of describing the temperature dependence of the electrolytes. So I think it's an area where there are good engineering models that are available, but to be predictive, we do need better models. So it's current research.
What you suggest for trade long range and short range interaction? What the way like mean spherical approximation, explicit solvent mean spherical approximation, or?
Well, if I had the answer, I would let you know. Yes, we have tried. We've looked at mean spherical approximation. We've looked at mean spherical approximation, say in primitive as well as non-primitive, or we call civilized models. But the
civilized models,
civilized models, yes. Let's all be civilized. It's a difficult problem. And what we've found is that when we think we're accounting for all the molecular details, the temperature dependence is not well reproduced by our theory. But as I mentioned, simulation also doesn't necessarily do a good job of modeling the temperature dependence. And in fact, I think we probably have pretty good agreement with the molecular simulation. So maybe there's some physics that we're missing out on. But the approach we're using, yes, has been based on a mean spherical approximation for the long range. For short range, we're using hydration of the ions. We've developed a brand new theory that allows us to describe hydration of a spherically symmetric site, or in other words, a spherically symmetric ion can be approached from any direction. And it's so we've had to incorporate multi-body interactions, and we've done that in a very, I think, clever, simple way. And so we're hopeful that that will provide us some of the answers.
Thank you. I think Pedro has a question.
Yes. Pedro is asking, Professor, how did your experience in Shell influence your research interests?
Oh, that's a good question. So when you're in graduate school, you're focused on a very, very narrow area. And I learned that at Shell, that you need to focus, you need to also have a bigger picture. And so it allowed me to step back. And one of the things I learned at Shell that I thought was really good was my boss would ask, let's say we solve a problem. Let's say we solve this problem. Of course, remember it was Shell, it's an oil company. But he said, let's say we solve, I don't know, wettability, the contact angles of oil water mineral systems. Let's say we solve that problem perfectly. All right. He said, how many more barrels of oil will that get us? Because in the end, that's what's important. And if you can, there are some problems that may be fairly easy to solve, and it may give you a few percent additional recovery, and that's worth billions of dollars. And then there are other cases where you could focus on a very narrow area, and to solve it, it might not give you a large strategic advantage. And so the idea is you need to choose your problems carefully. Yeah, basically that. And I think the other thing that working for an energy company gives you the perspective that that you're an engineer. You're not focused in one narrow area. If when I was at Shell, if I had a fluid mechanics problem, it was my fluid mechanics problem. I had to solve it. Now, certainly I could walk down the hall and find an expert in fluid mechanics, and he would spend a couple of hours with me helping me work on the problem. But in the end, it was my problem to solve. Same thing with interfacial phenomena, or maybe reacting systems if we had reactors. So it's I guess it's the idea that you should be dependent on yourself, kind of be able to and educate yourself in new areas. So that's kind of what I think I learned from Shell.
Okay.
Acho que Ingrid quer. Oh,
Yes,
I'm sorry.
yes.
I
We
think
have a few more
Ingrid
questions.
wants to ask something.
You ask or okay, I'll ask.
No.
Ingrid,
Ingrid, can you ask?
Yeah. Hi,
okay.
Professor, thank you for your presentation. Are you guys hearing me?
Yes, yes.
Yeah. Yep. Go ahead.
Thank you for your presentation. My question is in a specific point. You were telling us about the importance of the associative effect in the mixture of alcohols and hydrocarbons. So I would like to know if ethanol has a similar behavior as methanol in this case, in this study, because we are studying ethanol more here, because in Brazil we have a specific interest in the use of ethanol for inhibiting hydrates. So I would like to know if this behavior is similar or not.
Yes. So so ethanol is going to have similar behavior, and so in fact, let's see. I think I showed. Okay, so this was the butane methanol system. In this case, this is actually ethanol with normal hexane. And so, yes, the position of the azeotrope will shift. Ethanol, I expect to be more soluble in the alkyl or the hydrocarbon phase. Of course, that's important because it's only ethanol in the aqueous phase that inhibits the gas hydrate. And so as you dose the system, you need to know how much of the alcohol will be lost to the hydrocarbon, so that you'll know how essentially how well you've inhibited the hydrate, or how low you can go in temperature with the hydrate. So that the phase behavior, yes, is similar in ethanol, or here normal propanol, or one propanol, sorry. Yeah, so the systems all have maybe similar phase behavior.
Okay, thank you.
Yeah, thank you for the question.
More questions?
We have a few, but maybe some of them can wait to Thursday. But well, I have one more question, just one more question. It's from another graduate student. His name is Thales. He knows your work a lot, Professor Chapman. And he has, just out of curiosity, one question. It's not about anything you specifically mentioned today, but well, can I share my screen just for a minute?
Yeah, here, let me, let's see, I'll stop sharing.
Okay, thank you. He's asking about this specific paper of yours. He works with experiments, at high pressure experiments, and just out of curiosity, he wants to know if you still works with this experimental scheme, and he wants to know from you what are the most difficult to work with such a complex experimental scheme,
Right.
because you use this to measure, to model. Let me share, to model some. Should I share my screen again? Would you like to?
Sure, that's fine.
Okay.
Yeah, so so this is a combination. The paper ended up being most of this work. The experimental work was done by Matt Yarrison, and we were interested in publishing some of the work. It was somewhat delayed. It was for we worked with the Gas Processors Association to measure some of this data, and so Fuad, who's the first author, became aware of the data, was doing some modeling, and so it became a combination of modeling and experiment paper, even though the work was done several years apart. Matt Yarrison, I was very fortunate at the time. I had two people in the lab. One was Dr. Q Song, who had worked with Riki Kobayashi for many years. And so he was an expert in high pressure phase behavior. And Matt Yarrison was a student, and he is, now he's got his PhD, and he's a brilliant student who worked on this problem. And these are very difficult experiments to do. We had a blind cell that was rated to 30,000 psi. So let me think. So that's 2,000 atmospheres, or say 200 megapascals. So choose your favorite unit. So it's very high pressure cell. It was a 1 liter cell, 1 liter of fluid, and we could go to 30,000 psi, which I think is incredible.
It's a lot.
That's that's why they call it a bomb, I think.
Yeah, I agree.
We only went to 16,000 psi, but Matt Yarrison did the measurements. And with carbon dioxide, it was incredibly difficult, because with carbon dioxide, the O-rings, carbon dioxide, particularly at higher pressure, was very soluble in the O-rings. So the O-rings would swell, and we had problems with leaks. And Matt called many of the top experimentalists in the world to try to find out what they would use for O-rings with carbon dioxide, but he was never able to find something that worked well. So he redesigned the cell. It was a autoclave cell, but he and our lab technician redesigned the cell to have metal-to-metal seal contacts. And with that, he was able to operate at high pressure with the carbon dioxide. So what's done here is we're measuring water content in a hydrocarbon CO2 stream. And so you make up the mixture, and then you bubble the mixture up through, as I said, it's a 1 liter cell. So we had maybe 800 milliliters of water. The CO2 with, say, methane was, or pure CO2, depending, was bubbled up through the solution. There were baffles near the top to prevent entrained water, and it would flow through a moisture detector, a panometrics moisture detector, and it went through these U-tube with desiccant traps to capture the water from the system. And then we had a wet test meter, flow meter for the gas to determine the gas flow rate. And so what Matt was able to do is show that he got a very good agreement between the panometrics moisture analyzer and the desiccant traps over ranges that we could use the panometrics. So it was, yeah, very, very nice research. Matt Yarrison has gone on. He is now the chief thermodynamicist at the Jim Beam Distillery in Kentucky. So there, I just say there is great opportunities for chemical engineers. And I think the distilling industry is a great place to end up. So that's a bit of a joke. Well, what a great job to have, right?
Yeah.
The chief thermodynamicist at a distillery. So
I think Larissa wants to ask something, yeah?
Yes, we had a question from her, but Professor Chapman kind of answered it already.
Okay.
She was asking about CO2 and water mixtures, and how does this exchange mixture can be modeled by SAFT. Well,
so it's actually it's actually a difficult question to answer. And
yes,
so
it is.
one way is modeled in this paper by Wael Fuad. What you find is that there are many different ways that we could do this. Now, carbon dioxide has a quadrupole moment. The oxygens on the end are negatively charged, and the carbon is positively charged. So it's called a quadrupole. And that quadrupole will interact with the dipole of water. In this case, we're not including the quadrupole moment. There is work by Joachim Gross's group where they are including the quadrupole, and they also get very nice results. But what they're doing is or what we're doing is we're including attraction between the water phase and the between water molecules and the CO2. So it's like there's a hydrogen bonding type interaction between the two. And so we're able to model the phase behavior very well. We would like to include the dipole in the water, the quadrupole in the CO2, and the hydrogen bonding. You can very quickly have too many parameters or more parameters than you can necessarily fit. And there are questions about, are you double counting in the different models? I tend to think of these as short range interactions versus long range interactions. And so I think as long as you're able to divide them into short range and long range, then you can do this sort of modeling and you're not necessarily double counting. So that's, that's the answer. It's still a difficult problem. There are issues with CO2 water hydrates and water content in carbon dioxide in the hydrate phase. At higher temperatures, we tend to need to include this additional hydrogen bonding interaction between water and carbon dioxide to match water content data. At lower temperatures in the hydrate phase, if you include this attraction, say hydrogen bond between water and CO2, you'll overestimate the water content in the carbon dioxide phase. And so maybe it's better to account for it through quadrupolar and dipolar interactions. That's still up in the air. I haven't seen anybody kind of resolve this.
Interesting. I mentioned Richard Elliott. He's with us.
Yes, yes. Hi,
Oh,
hi,
yeah.
hi, Walter. How are you?
Hey, Richard, how are you doing?
I'm fine. Yeah, so I gave a lecture to this graduate group last week, I guess, and so again, trying to keep things kind of basic, but when you talk about H2O and CO2, there's a, if you look at it from an electrolyte perspective, there's actually a reaction, a very specific reaction between H2O and CO2 that you didn't mention anything about. I wonder if you want to mention something about that.
Yeah, you're absolutely right. So I guess I was mainly thinking in terms of what's happening in the gas phase between the water and the CO2. But certainly in the liquid phase, there's electrolyte reaction. There's you form hydrogen is lost from the water to the carbon dioxide. You form HCO3 minus, and I guess it's OH. But anyway, the HCO3 minus can certainly affects the pH. It can affect the phase behavior. And so what Matt Yarrison did in his model, he modeled the same system, but used a cubic equation of state because the industry was interested in including or modeling the system with a cubic equation of state. So in order to model the aqueous phase, it was necessary to include this chemical equilibrium. And so that is it can be an important contribution. Yeah, you're absolutely right.
One more thing, I guess.
Yeah.
So H2CO3 is generally recognized as a separate species by itself. You know,
right. This carbonic acid.
Right. So, but if you were to represent that as just a kind of a regular SAFT interaction, that specific solvation interaction would show up as a kind of a chain of H2O, CO2, dimer, trimer, tetramer, those kind of things. But the H2CO3 is kind of distinct from that kind of long chain, that specific combination.
Right.
Is that something that you have a way of recognizing within your theory?
That's a good question. In fact, one of the Ken Cox has suggested that one of the issues that we're having with water content and equilibrium with hydrate could be related to this carbonic acid species being present. But no, I don't have a current way of dealing with that species. Have you done anything with that?
Generally, I just write down the chemical reaction, superpose that on the regular SAFT-like analysis, and just do it both at the same time.
Right. Yeah. Actually, I was recently looking for formation data for carbonic acid. Do you have that information?
Yeah, it's pretty much available if you look in an electrolyte compilation. So the OLI compilation will give you that. And we actually have a sample problem on solving that system, just the chemical aspect of it, in our textbook.
Fantastic. Yeah, that would be interesting to look at.
Yeah. Tiago and Yuri, I think it's time we stop, no?
Yes, yes. I think this was a very interesting lecture. Some of the students already knew something about thermodynamics, statistical thermodynamics, but many others didn't. So I think it was brilliant and it was very didactic. I would like to thank again Professor Chapman. And well, we will see each other next Thursday. We still have a few questions, but we will not going to bother you anymore today. Thank you very
Well,
much, Professor.
Well, thank you. Thank you for the invitation. I hope it wasn't too basic for some or too advanced for.
No, it definitely wasn't. Many students are in this part of the learning process, but some others already know your work. But that was awesome. Thank you very, very much.
Certainly. All
Thank
right.
you, Walter. Thank you very much.
Enjoyed it. Thank you, Fred, for the invitation, and yeah, look forward to talking to you all on Thursday.
Yep.
Yeah. See
Bye-bye.
you.
Thank you.
All right.
Thank you.
Yeah. Take care. Stay safe.
Stay safe. Take care.
All right. Bye-bye.
Bye-bye.
Bye-bye.